And okay, so since we're recording now, welcome again. Week number 4. Just to remind you where you are, this is a yes.
Sorry, we just came, but is the 26th now the exam date for the first one?
Exactly.
Okay, because we have at the same date another exam.
Good.
I don't know if this is.
Let's talk about this afterwards. We yeah, you might be able to push it somewhere. No, okay, let's start over again. Wait a minute. To remind you where we were, quantum field theory, week number 4, we started by giving some motivation why we want to do it. There's an obvious reason. If you have a classical field theory like electromagnetism, you might want to quantize it. Say you want to describe the photoelectric effect, then you need photons. It doesn't matter how much energy is there in your electromagnetic wave in total, which is the intensity, to kick out electrons, but you need to know what's the energy of the individual particles in your wave, the photons. They have to have a high enough energy. So you need the photon picture. So that's one reason. That's the obvious one. Another less obvious one is if you want to combine quantum mechanics with special relativity, then you're led to consider multi-particle theories. So we had this problem with the particle production problem. I don't know, we discovered that in the formalism of relativistic quantum mechanics, there is something built in of particle production, the time paradox. This was week 1. Then we saw when we write down a theory for multi-particles with an unfixed number of particles, we naturally have a field theory there. That was week 2. Week 3, we talked about an example applying these things. This was very nice about this superfluid. I made up a little story where you can apply this creation and annihilation business. And then we started with the classical relativistic field theory. It's basically a restart because they went back to classical theories. And there we talked about the action as at a distance problem. The Newton's theory of gravity, for example, is a theory with action at a distance. The planet there knows instantly what your planet here does because there's no different times in there. It's all happening at the same time. And that's theoretically a perfectly valid theory, but it's not what is observed. The planets don't go exactly in ellipses, but they are kind of rotating ellipses. And that's because it just takes a minute, 8 minutes before the signal to arrive at the Earth, the location of the Earth. So then we had this problem that there's the speed limit. The speed limit necessarily led us to special relativity. All the observers experience different lengths and times and coordinates in the Lorentz transformations. This is where we are. Let me quickly repeat a little bit more what we did. So this is number 4. Classically, relativistic field theory. I'm summarizing some things and then tell you what we're going to do this week. Yes, for 2, what's the Lorentz? Transformations. And we wrote them eventually as now we think of this. I want to keep. I don't want to keep this. There's this combination C squared minus x vector squared is the same for any observer. The x might change. The x is the location of an event, the t is the time of the event might change, but this combination is the same for everybody. And then people say, okay, let's have Minkowski space. So this is the universe. Here's x vector. You think of it as a three-dimensional volume, and then you have a CT here. And this is everything that happens everywhere at any point in time. This is not just now. This is everything, all the times. Any point in here is an event. I did bring color, so let's use the color. So that's an event. And if you're an observer, you just pick a coordinate system in there on this plane, and then you can decide what your clock and your meter stick says. And we agree for simplicity that there's one particular event, this one, where every observer has the position 0, it's the origin of your space, and your clock shows 0. So that's supposed to be for everybody. So the x and the t-axis go through this point. And then I have a different observer. Yes, these axes. Right, and now you have your event, and you can go there. So if I go here, I have these coordinates, go there. And got numbers, this is the x, and this is the x prime, and so they change. I'm thinking this is also something I have to say. It's a passive coordinate transfer. It's a passive Lorentz transformation. There's an active and a passive way of thinking about the same thing. This picture is the passive one. You have your universe, and there's something happening there and there, and then there are two people looking at this thing, this scene, that time evolution or whatever is there, and that's passive because the observer changes. You could have something else. You could have a coordinate system, and then there is something in your universe, and that's here. Now you do a Lorentz transformation. Basically, you give a different. This is moving now. Same coordinate system, but things start moving. Then I push. This is active. It's the same matrix though. But the sign, very confusing sign. So I want to, for now at least, think about these transformations as the passive version. I have different observers looking at the same thing. And then the Lorentz transformation is this x prime mu, the matrix lambda mu x mu, and these are the coordinates for one person of one event, and these are the coordinates for another observer of the very same event. And in this matrix, I have. I can write this down right now. This depends on lots of things. It depends on all times x. So this thing depends on all the boost velocities, the relative velocities, and the angles. If I am in 3 dimensions, how many parameters do I have? No, this one's battery. I don't know here at all. How many parameters do I have for Lorentz transformations here? 1? 4. Count 4 for me. Oh.
T, x1, x2, x3.
Basically this thing here, x mu is ct x y. That's what you're counting, right?
First, the Lorentz system.
But that was what you were counting.
Yeah, and then it's 6.
Right. So this space here is the 4-dimensional space. This is a vector space. I can add and subtract and multiply and scale, and that's 4-dimensional. And I call this Minkowski space, and this is R1,3. And there's lots of places where again counting's confused. That's why I want to say this one more time. So this is the 4 from here. Now you were counting how many ways have I of changing coordinates without spoiling the fact that I'm an inertial observer. So all of these coordinate systems are for inertial observers. So observers, they don't experience any force. And then you said 6. So this has 6 parameters. And you could think of them as rotation angles. Like this is just normal space, 3 rotation angles in 3 dimensions. And then I have 3 ways of pushing the chair into X, Y, and Z direction. So I have 3 velocities. So these are the 6 parameters. It's really close here. Yes.
Why do we have 6? Like, isn't it? I would have thought that we have like 3 directions of velocity.
3 direction of velocity? Yeah, let's write them. So the 6 parameters. It's a little hard because we have to agree what this is actually the story of the day, how to parameterize them, but let's roughly 3 parameters. So that's basically 3 velocities, yeah. So that's easy, right? You can move the person in X and Y and Z direction or any vector. So that's basically this. And now the angles, are you talking about asking about the angles? Oh, you're not asking, you're asking why not 3? Where's the other 3?
Yeah.
Oh, because that's basically the boring stuff. You could say that isn't really special relativity. This is just rotating things. If you have a system that is rotated with respect to someone else's inertial frame, it's also an inertial frame. It's not moving though, it's just rotation. Basically to make things more,
Okay, yeah.
I was gonna say complicated, but complete, yeah. So plus 6, plus 3 angles. Relative angles. So I have one coordinate system and then another, and then I ask what's the angle between your X and my X axis, and then we'll be counting this in a minute. Yes. Why am I excluding this? But if it's boring, so these Lorentz transformations that only have these relative angles non-zero are called rotations, and those, the rotation angles are 0, are the more interesting ones. They're called boost. Boost because you push the thing, boost. Still, why do I include them? Because they come naturally when I ask for this to be invariant, right? If you don't mess with the time, just because this square here, the length of the axis is the same, so it's harder to exclude them than to just have them there. So that's the stuff. If you go down in your universe, if you have only like a 1 + 1 dimensional universe, you have different counting. You have no angle in 1 + 1 and in 1 boost. So that's my favorite. This is the easiest. And so I'm not sure that I'm going to go into the upper lower indices business. Well, the metric, let's write on the metric. So this minus sign you take into account by saying I have if I want to write a scalar product, then I have to put in between my x-axis, I put a metric. So that's your scalar product, x squared. And the eta, you is a diagonal matrix with the entries +1, -1, -1, -1. And then this is exactly this combination. And lowered, so these two together is an x mu downstairs, d2 is x mu downstairs, and so on. I have the feeling that I was much too slow last time. I told you things that you knew, so I'm not going to repeat that one more time unless you'll ask me. Now, these Lorentz transformations had funny properties. What's the determinant of this matrix? You remember, that's important. See, if this was an order exam. What's the determinant of yes?
The proper one had 1
Ah.
and the improper had.
Exactly, it could be both. It could be plus or minus 1, but nothing else. And well, that's it. Okay, I'm writing this in the other interesting was what's the sign of the or the size really, more than the sign of the 0, 0 component, the one that relates time and time, that is either larger or equal 1 or less than equal -1. I have to, before I really make use of this and turn this into a picture, I have to ask whether you did your homework. We're supposed to show that the Lorentz transformation, the set of all Lorentz transformations, is a group, and you did that, right? So a group means you perform 2 and then 2 Lorentz transformations. So you pick one of these matrices that satisfies this. In fact, these 2 things followed from having this invariant. So which lambda keeps this intact, and this was this object. Oh no, this is a mess on the blackboard. Thank goodness this is just a reminder. So this was the condition, and these two things followed from there. So you pick one lambda which satisfies this, and you pick another lambda that satisfies this, and then you build the product of these two, and the product satisfies this. This is what you show. And if that happens, also the identity should be a solution, and you should have an inverse, and then you call it a group. Can you give me an example, honest question, of something maybe from everyday life? You have an action of a certain kind, this kind, you have another one, but they don't form a group. If I sit down and think about it, I feel like everything is a group. I do something, I do it again, or slightly different. I could have done the same thing at once, right? I spill one glass, I spill another one, I could spill both. I write, give me an example.
Not that easy to unspill a glass.
Okay, so inverse, yes, good. Thank you for saving my example. I came up with something cooler, but I want a second example. So before I give mine away, it was more the composition. Like if you do something and you do it again, then you could have gone the whole way. Because maybe I'm thinking too restricted, because I'm always thinking in moving. If I push it there and then I push, I could have gone straight. Yes.
Like subtracting is not associative, for example.
Oh yeah. This is also yeah. It's also yeah. It works. It's abstract. I was thinking of who plays chess, because I'm thinking pushing. If I have a chessboard and then pick a figure, the rook, say something easy, and then you can move and then this way, as you want. You move again, say back. Okay, you could have gone there straight. So a valid move and another valid move along one line is a valid move. But you could have gone like this way, and then these two together, two valid moves are not valid move. I thought it was pretty cute. It's like you have the Lorentz transformation, which is valid, another valid. You do both one after another, and it's also valid. But that's sort of something lucky, maybe, or something special, celebrate. It's not always that you do something of the same kind, It's a group, and it's special. And now this thing, the Lorentz transformation, the set of Lorentz transformations, is not just a group. It's a Lie group. What is this? So if you have one of these matrices that do a transformation for you, then you can find another transformation which is arbitrarily close to the first one. So basically you rotate by 3 degrees. You can also rotate by 3.0001. So it's continuous. So that's the thing. Your group elements are not just, you cannot just list them. They're continuously many, uncountably many, and they're continuously. So there's some continuity. So a Lie group is something that looks like a geometric object. They say it's a manifold. So I'm going to draw the manifold here. This is now, I like to draw this too big. I like to draw manifolds as potatoes, because they have this kind of weird shape, but they're smooth. So this means any point, and this is a six-dimensional surface because I have 6 parameters. And anything on this 6-dimensional surface is a Lorentz transformation. So I say this one is 1. This happens to be the identity, because I close it. But then there are others, and every point is one of these lambdas. So here I can say this is one particular lambda. Some special, and then there's one right next to it. However, that's not, this picture is not everything because of these properties. That's where I was going. If I have the choice that my lambda has a determinant of plus or minus 1 and nothing in between, I can hardly go from 1 with a plus determinant plus 1 to 1 with a negative 1 in a continuous fashion, right? Because I have to jump there. There's nothing that brings 2 of the different kinds close or like along a path. So there will be a copy. There will be, this is the set, because that's the identity has determinant 1. This I call the Lorentz transformation, the set of Lorentz transformation L plus with a determinant plus. And then I have a copy. That should be the same finite there. Yeah. There's the thing above. And this is the one with the minus sign. And yes, and they're disconnected. But also every point here is the Lorentz transformation, however, one with a determinant minus 1. And then this thing happens. You can't also go smoothly between these 2 regimes. So I have to pick, what is this? This is actually, because it's the one has, of course, the one not the diagonal, so it's the top component is equal to 1. So this needs to be in the first kind, so it's actually proper orthogonals. And then this, okay, now this is confusing. Now I changed my, what do I change? Let's see. So I have 4 hatches, really. 4 connected components, but they're disconnected from each other. And then every combination, just have to see what I'm going to write. So let's say we switch time here, we switch place here. I think in my notes, I want to send pictures in my notes. I do parity here, so this remains, and I go minus. And then this is time, so this is minus and down, and this is whatever's left, plus and down. So from here to there, so every point that sits here, I can map with a Lorentz. Oh yeah, this is the fun part about these Lie groups. It's not just that every point is one of these things. I have a map on these potatoes. If I take 2, then these 2, of course, map somewhere. And if I map, well, I can map this one to his friend over there. And that is done by the P, and P is the diagonal matrix, plus 1, minus 1, minus 1, minus 1. It's a Lorentz transformation, but a very simple one. This was also one. The diagonal matrix 1, 1, 1, 1, and this is also 1. And I call it the parity transformation P because it flips the space. So it just flips the determinant, but it doesn't change the sign. Yes.
How would this look in 2-dimensional space? It's like, then we don't change the determinant if we did something like.
What
this.
two
If we-
space,
two
2 plus
sorry,
1.
yes, yeah.
Yes, you don't. Yeah, you don't. Then it's a little bit, let's see, in 2 dimensions, plus minus. Yeah, I don't know, it's just a little different. I find it annoying too, because now I want to do time reversal, so I want to go from here to here using the t, and t switches the time. Plus, plus, plus. There's no one, you understand. -1, +1, +1, +1. And that switches the sign, but it also messes with the determinant because it gives you one extra. So that's why it looks kind of weird. Here I'm changing just the plus minus sign. Here from here to here I change both plus minus and the error. And if you have 2 dimensions, you have to just be careful with then the parity doesn't fit in. And so in here I have my t. This is the t transformation. This is the p transformation. 1 times the p is the p. 1 times the t is the p. And then I can also have a 2t right at the end. And reversal. So I can go also across both. Anyway, so this is what I wanted to draw in the picture. I didn't do this last time. We discussed these patches, these properties, but now this is how it looks like. All good. Now we can happily transform events, x's, or call them a or whatever. We can, these 4 vectors we can transform. But I remind you, we're doing field theory, so we don't have events. We have field. How? Yes.
One more question. In the beginning, we said that the Lorentz transformations form one Lie group. Are these now 4 separate Lie groups?
No, this is all one group, and then you call these things the connected components. It's just a disconnect. It's one object. It's all the yeah. It's a funny manifold, but it's just disconnected.
So there are like points or like elements within the group that can't be reached by other elements within
They can all be reached, but not
Not
smoothly by varying the parameters. Yeah. By the group actually can reach them. But you can also focus on this upper left. This is special because there's the identity, and I'll be talking about this all the time today. But yeah, you can define various things, but the usual way of thinking is that is the entire Lorentz group of Lorentz transformations, and they have the different connected components. And now the fields. How do we know and figure out how fields transform? This is completely arbitrary. This wasn't somehow on physical grounds we could write down these explicit matrices, but now how does this work? The headline is representations of the Lorentz group. And so my question is, how does a field, how do fields take this phi x, where by x I mean, as always, the full 4-vector transform under the well, let's think about it. Let's say this is this universe from there. And I have a field, which means for every t and x vector, I have a value. And for some reasons, in this area here, there's a lot of value, and then it falls off. I don't know. So I want to basically mark the point. It's not a particles of the event, but there's some profile, right? I can see that, I can go and measure it. So here's maybe the maximum of it. Now someone else comes with his and her meter strips, and so as the transformed one, x prime c prime. And then she wants to describe the same universe with the corresponding field. But that field should take as arguments the current coordinates, the prime. So that can't be the same phi, because if I stick into what we had, this number, so where's the maximum here? In the yellow one, it's here, and here, and there for the other one. If I stick these x's, the prime, if I stick the prime values into this field, I'm not ending up at the maximum. This into here, then I'm off. So it's a different field. All I'm saying, you have, if you're a different person, you have a different field. You have your own field, x phi prime of your coordinates. But then what is the value? If this is just what it is, if this is the universe, then you want to say, do you say, can you argue? I mean, what would, to describe the same physics, the same object here, the same red color distribution, the yellow person uses a function phi prime of x prime, and the white person uses the phi of x. And how are this phi of x and this phi prime of x prime related if it's supposed to be the same wallpaper, the same color?
This should equal phi of x. If
Yeah,
x
yeah.
prime and x are transformed by the ones.
Exactly. So wherever this x goes, right? The x by our Lorentz transformation is moved to this x prime. Isn't moved. It's passive. Sorry. Hey again. So I have a location in the white coordinate system, which is special, and that has coordinates x prime. In the other one, it's the same special location, and there the value should be the same. So that's the transformation law of this colored blackboard. This is how a field could transform. There you have. How does the field transform? There. Is it always like this? No, it's too boring. Then you can have much more interesting things. Later we'll have a term for it. This will be a scalar field. We can have a collection of fields now. And the collection, these different fields of the collection are the phi I of x. How does this transform? So think of this index I as sort of maybe a vector index. So now I don't have a number everywhere, but everywhere I have several ones, and you can draw them as whatever you want. For simplicity, I draw an arrow. So it's really like a vector field. But at this point, I have different components. This is my phi 1, phi 2 makes a vector. So it's, why not, right? Vector is very special, very restricted, but just for illustration purposes, if I have a collection, then I can draw this collection as something that points. If an x phi 1 is large, and in this direction 1, I draw a lot. It doesn't even need to be 4 numbers here. This vector is not a vector in Minkowski space. This is whatever sits at this location. It could be a 20-dimensional vector space, and these are 20-dimensional space, and these are the 20 fields. Why not? So, but then now if this space, this 20-dimensional space, has something to do with geometry and with space and with time, so being like literal vector, then yellow, then I have to take this arrow seriously. And in this new coordinate system, the components are very different. For example, here this shrinks, while down here was longer. So it's not just that it's not this. It's not phi prime I x prime. It's phi I x. That would be if it doesn't have any geometric meaning and all the components behave like scalar fields, like colors. But if they have a geometric meaning, then I should allow the different ones to mix. And I'm going to allow them to mix in this way with the matrix rho ij phi j of x. And there's a little gap because I want to this is not a constant matrix. It depends on my Lorentz transformation. If my x prime is a lambda, then this depends on my lambda. And here I'm getting, right now, I would like, don't copy, I would like to write lambda, because you have your Lorentz transformation and then you decide whichever Lorentz you have, what's your role. But in my notes and everywhere else, I have it a little more abstract. We have a G, which is the set of parameters basically. It's the abstract, the idea of your Lorentz transformation. It says, I want to move this way, or that's the G. The lambda is the matrix that does this action on your axis. And then this takes the same G, that's the Lorentz transformation abstractly, and makes the transformation of the field. So they're still connected. Doesn't make any sense. I have this is the G. The G is the abstract Lorentz transformation, and this is the matrix transforming the 4-vector U to this G, right? You call me and say, turn the chair 2 degrees. Then you gave me the G. That's just the order, what you want. That's the transformation. And then I go and do it. But I have to do it with sort of a matrix. And then I pick the matrix that does exactly the rotation. And the chair was that. Now I have a field, which is different from a chair. It's something in yet another space. But I want to do what you said, turn it in 30 degrees, I guess it was. Then I have to pick the row that does that. So they are connected by this abstract thing in one. See, I'm not saying this yet, but soon I'll be calling these representations, right? This is lambda represents the transformation on the axis, rho represents the transformation on the fields, but I haven't said that yet. Well, I did, but you know, I thought it was getting confusing if I don't say it, but it's also jumping ahead. Now, so let's just say that we have a set of fields and they can mix. You might wonder why. Where is this coming from, this index? What kind of index is it? Like, is it really 20? Where the hell do I get the rows from? What's their, is there a condition? Can this be anything? Am I losing completely ground or, yeah. And so that's really what it is. There is a strong restriction on what you can have, and we want to figure out what the restrictions are. These are then the representations. This I want to keep. Now, we figured out that the Lorentz transformations are a group, any group, and I will get it. So the group, let's try this. If I take a lambda of 1 transformation and another multiplied rho, then there is a Lorentz transformation here somewhere, which would bring me from the start to the finish, and that I write like this. abstract composition law of Lorentz transformation. So somewhere from you have one and another, and then because it's a group. What's the point? It's not chess. The transformation of this combined one is the product of the individual one. So this is the matrix multiplication multi of the Lorentz transformation corresponding to 1 and 2. And now I don't have any space left. In order to figure out what kind of restriction I have on my row, let's perform 2 consecutive Lorentz transformations on this field, on the field. So my Lorentz transformation that I want to so I go twice. Moving my coordinates twice. It's x prime. This is the lambda of G1 times lambda of G2 times x. By the way, that's also not really necessary, but usually I count 1, 2, 3, 4 this way up. And what I do first, I count 1. First in the morning I do this, and then. But here it's the other way around. This is me in the morning, and then I first do a transformation with G2. No, the action is the first one is to the right, but it looks kind of neat. 1, 2, 1 from reading from the left. But still, I want to point out this is what's happening first, and so then this is lambda G1 after G1 after G2, and I want to act with these two on my field. So phi prime of x prime with the indices I is, by definition, it's phi prime I of what I stick in here, lambda G1, lambda G2 x. So this is what it is. And now, with this rule there, here, see, this is inside. There is a phi of lambda x, which means you can remove the lambda x and put a row in front. So this, by the above law, is rho ij of G1 phi prime j of the other one has to wait. So does it make sense? So I removed the first one. Yeah.
I'm kind of lost in the track. So are we still talking about the same thing that you were showing in that diagram?
No. This was just to motivate this rule for the general transformation of fields. The one where the row isn't there, or it's the delta, it's an identity matrix. This was the first naive thing with the color, and this is a set, and we can allow for this thing. And now I'm trying to figure out what restrictions do I have on these matrices row. At this point, it could be just anything, here, 20 by 20 matrix, put numbers, whichever number you want. And I'm trying to find out if there's a restriction. There are strong.
We're still looking about like one component of this figure.
No, we have the set. Now we're working with the set. And I have to, in order to figure something out about these rows, the trick is to look at two Lorentz transformations. I just do it twice. I do it twice in two different ways. And if I do it twice in two different ways, I get an equation. Well, I do it, yeah. let's see, at this point, you're wondering, rightly, you're wondering, what am I doing? And, now the idea of this computation is to get the transformation of this in two different ways, once for this and once for this, way of writing it. Basically using the glue property of the Lorentz transformation, and then compare the result. Does this technically make any sense? Have I, like, forgetting about whether this is philosophically right, have I done a computational mistake? You don't even see what I'm doing, right?
I'm just like visually, it's not coming together. Like what we're doing.
Visually it should come together. There's a phi prime of lambda x. So this thing is the positionist Lorentz transform. And this is the same as the original field of the original coordinate, but mixed up the component with that.
So you just look at a set of fields that transforms this way.
Exactly.
Okay.
This is, and this is basically my own, I mean, not personally my own, but this is what I gave you. I motivated to say this is what we want. In fact, yeah, it's pretty general. Well, it's a linear transformation of these fields, but it's fine. The most general linear transformation of the field of this set of fields. And I'm not picking a constant matrix, I'm picking something that may depend on this Lorentz equation, and I'll figure out how it depends on. Now, if I do this twice, you can think of this object as being an x prime, right? So then you have phi lambda x, well, that's rho phi without the lambda and just the x. So then you have here just x. And now I do it the second time. The rho is already there of G1. And now this pops out, rho jk, G2, phi prime k of x. This is one way of doing it. Or the other phi double prime I of x prime prime is with this thing. Phi prime prime I of lambda G1 after G2 x. So now I have only one matrix and I go straight to the x. Now out comes rho ik G1 after G2 of phi k x. Who did this? Were you wondering? Yes. Yeah, because I have transformed it. You can just shout if I'm doing nonsense. Let me know. I noticed this now because I want to compare the two different ways of doing it. And left hand side is the same, and on the right hand side I have my field phi k. X is also why I call this k and not j. So the one field is the same. So if everything is the same, then this is the same. This and this thing is the same. So I want to write it there because it's the same thing. I get rho I j of G1 times rho jk of G2 is equal to rho ik G1 after G2. This is a condition on those matrices. Yes.
Can you say again that why in the second on the second part, why did you just have one row? Why does
Oh, here in the second way of doing it?
yeah, but why does one row does two primes my
Exactly. Because I have the two transformations. I start with this x, then I go to an x prime intermediately, and then with another transformation to x double prime. But I could have gone all the way from there to there with this combined. This is the point. You have
but
two.
why does the row can also make the double transformation.
Yes.
Where there's only
we
one
never said
row
any-
can
yeah.
maybe double transformation on the
You
field.
said, we never said anything about the row. How is the row now possibly doing what the Lorentz transformation does? Because if I write this, there's just one lambda of some abstract Lorentz transformation. This is just a G. It's a G after another G, but since it's a group, it's just one Lorentz transformation in there. And so then, if it's just one, out comes only one. You might wonder, this is a trick. You wrote K because you wanted the K. Exactly. I wrote K. If I had just copied blindly what is the general thing, I would have written a J. By the way, does it make sense? This is a matrix multiplication. Have you wondered? This is a sum, Einstein convention, basically, right? And oh. Now, here I should have written maybe this, but then how do I compare the two things? Apple and K's and J's. So I want the same. So that's why I rename it here into K. And now this is the same, and therefore the yellow underlined. It doesn't know it in advance, but I'm deriving that they're the same row. Yeah. It just follows because the Lorentz transformations are a group. And the rows are essentially the same group. Or people say they're not the same group, they're saying it's a different representation of the same group. So row is and now this is the definition of the word, a representation of the Lorentz group. Because it satisfies the same composition law as our lambdas. And these lambdas are also just matrices. So this is really just the same thing. These lambdas are really also a representation of the Lorentz group. But this is what we started with, and without the lambdas, we would have never ever found the Lorentz group. We call this thing the defining representation. So, depending on who you ask, but most people say a Lie group always has a defining representation. There is some abstract stuff where people built the whole theory without that, but you can show that it always exists in, yeah.
So the defining representation is kind of like if you really wanted to, you could use the lambda to refer to the Lorentz
Yeah.
transformation group itself.
Yes, exactly. And that's where it's getting confusing because what is this potato now? Are these the abstract group elements G, or are these the lambdas? And it's really the same thing, basically. Morally, it's the same thing. Technically, maybe not, because one, like an abstract thing, the other one is a matrix, so you can write down rows and columns. But since that defines what's going on, it is the same thing, really. So the logic was like this. We as physicists in particular, we start from some physical observation. In mathematics, you would just say, oh, why don't I study all the matrices that leave this thing invariant? But we have a reason for it. And then, well, even more. Well, when you say what eta is, so let's say that, and the mathematicians say, okay, you have this metric. What are these transformations that leave this invariant? And then you get you have the lambdas, and then you know how to combine them. So then you pick some parameterization. Let's do this. So you have objects that satisfy this thing, and it's not just one, it's really many, all of these in this picture, and you have to parameterize them somehow. So pick two, this one, and then they get combined in this fashion. And then you can figure out where sits the result. Somewhere else. There. Now, if you want to build your own representation, what you have to do then is find a row, a mapping, so your own, now do your own representation. So, yeah, building. Your own representation. Then you would just have to find a mapping. So here you propose a mapping. Propose a mapping from the group to the matrix to linear transformations, and check whether this is satisfied. And how would you figure out whether this is satisfied? That's tough. Because you don't even know what you're doing. I mean, if you pick a transformation, another one, okay, fine. You have proposed a map, you can find these rows, but what do you compare this with? Well, you have to compare it with this thing, so you have to know how to combine them. And two arbitrary Lorentz transformations are hard to combine. I find rotations hard enough with these Euler angles, like you have one rotation around this axis, then one rotation around this axis, what's the combined action? It's some weird axis, and it depends on the directions of the rotations, it depends on the angles, it's just awful. So it's hard to check whether your proposed mapping is actually a representation. Can we agree on that? It's hard, because it's hard to get this explicitly. And therefore, we've come here to do this, to find these representations. Wasn't the headline representation of Lorentz? Yes.
What about existence of all this? Like Lorentz transformations and stuff and fields and everything. I mean, you just postulate their existence, don't you?
Yes.
But when are we gonna consider, are we gonna do that later? I mean, just maybe by giving some examples, giving some
Well,
explicit
we'll
ones.
certainly see examples and see this is that they exist. Yeah. In fact, so let's give the answer. What comes out? Yeah. Well, there's lots of stuff. In fact, this is not even a compact group, right? I've been drawing these things as if they were like spheres or deformed spheres. Now they're saying global. This group is non-compact because my velocities can be arbitrarily close to C. Yeah, so yeah, it's not a rotation, but this can the boost, the momentum that you put into there can be infinitely large. So it's actually something more open, but I couldn't draw this. Now I'm getting somewhere ahead of myself. Let's do a simple one. There is, for example, this. I'm going to propose one, and I say this is one. So for all G's, it's the same, just for fun. I'm proposing this. Maybe don't copy it. But then I can check that this is true, because if I go row of G1 times row of G2, that's really just 1 times 1 is 1. That is row of whatever. I didn't know what it is, but whatever it is, it's still going to be 1. So that's a representation.
You wrote G.
Did I write G? Where they're they look so similar. So that is in fact a representation, and it's the only thing that I can actually verify. It's called the trivial representation. And you think, oh, this is dumb, but no, this is the scalar field. This is what we had when it doesn't transform. If you just want a single one. So that doesn't, it'll be one of the three cases, the scalar field, then the spinor, and then the vector. So the scalar we already have. And then the list is like this. So that's now the answer. So let's put there. You have something that you call irreducible representation. Oh dear. Let's write them down first. What the answer is. So the list of all irreducible representations is labeled by two numbers, which I call SL and SR, and they are like the spin quantum numbers. In fact, they are spin quantum numbers. Half integers. That's the list. And so a pair, right? Did I write two? By two. So you can and they have the dimension. Well, they write irrep. The irreducible representation is short for irrep. The irrep is short for irreducible representation. SL, SR has a dimension 2SL plus 1 times 2S. Let me give it a name. Dimension N 2SL plus 1, 2SR plus 1, which means that your row, the representation row that we are writing down, which has these two labels, SL, SR of G, this is an n by n matrix. So if you have now whatever I wanted 20 fields, right? Then my representation better be 20. Can I get 20 out of this actually? 4 times 5. I guess I can. Yes.
In our original
Okay,
case,
sorry.
we only had like a vector that transformed. Like, doesn't this like give a hard limit on how big the dimension can be, or like even the like I don't
Hard
know, like,
limit? No.
no,
Because you can count. Here's my table. If I write S L here, then I have 0, 1/2, 1, and so on. 0, 1/2.
But we have a vector that transformed, and I don't know if it has 3 or 4 dimensions, I'm assuming.
Well, let's see how many dimensions we get here, right? So 0,
Yeah.
both is 1. This is the one-dimensional representation. That's a trivial one, in fact.
Yeah,
It's the 1 by 1 matrix. This one there.
yeah,
So 1 is there. What do we get here? Left is 0, so I have a 1 there, and that's a half is 2. So that is a 2-dimensional representation. Very easy. So I have a 2. This will be our, if you know, Weil spinner. In fact, the right-handed Weil spinner will be these two. This is just flipped. It should be a metric table. So this is just 2. It's a left-handed Weil spinner. And what's this? That must be this times this, right? So it's a half times 2 is 1 plus 1 is 2. Same that 2 times 2 is 4. And this is your
this is the one that I'm like,
that you wanted.
I'm not sure if I wanted it. It's just like a picture that you drew that you like erased already.
Oopsie.
It was like from, no, just.
The one with the vector there.
Yeah, like originally we started with like that the row ij transform a vector.
Yes.
It's just like row ij.
Here was, this is what you meant, right?
Yeah.
By I.
Yeah,
And I runs from 1 to n, that very same n there.
what can it be? And or like, okay, maybe.
I have a collection of n fields which I can put into a column. And now they mix
Okay.
with a big row in front, depending on the G, and the row has the same indices. And now I'm telling you, I haven't done anything yet, we will, hopefully, that I can give you a representation of all these sizes. Let's go on. This is 3, this is 6, this is 3, 6, 9, I guess. So all of these sizes I can give you 7. That's sad. I guess I should be able to give you 7 up here. Yeah, I can give you 7. I can give you anything.
It's just, I don't know, it looked a little bit like this vector by I is like somewhere in our space, like in
Right,
the
that's it, that was just a side remark, but it's important. You have your sort of your Minkowski space, and at every point in this space, you glue another vector space, this field.
Okay.
In fact, your Minkowski space here is the base manifold of your universe, and then you have fibers at all the positions of your, and the fiber can be any other vector space. And the field is then section to the fiber. Now, this is the answer, so that you don't go home without knowing the answer, because I feared already we wouldn't get anywhere. The reason why the homework exercises aren't online yet is because I didn't know how far we're gonna get. I was hoping to get further than my notes, and now I'm realizing we might not even get through it by tomorrow. So that's why I'll decide later how much homework exercises you'll get. Now, let's try to divide this thing. We kind of do need the parameterization G of lambda, or lambda of G. And let's just write them down. So let's write try to write lambda of G as explicitly as possible. And so we have these 6 parameters. And let's just do one at a time. Let's say we have a rotation around which axis? The x-axis, why not, right? A rotation d around the x-axis through an angle alpha. This is so it doesn't do anything to the time. It doesn't do anything there. And then the x-axis, because we're rotating about the axis, is also not affected. And then y and z mix into each other. So you have cosine alpha here and there. And now it depends on whether you have an active or passive. Whether you have a passive one, so it's the minus down here. We can draw the picture and then you can convince yourself, but it looks like a rotation matrix that you've seen before. And then the others, I'm going to write one more. So different axis, but the angle I call alpha still. And I have the one here, and that's a cosine alpha, and that's a 0, and that's a minus sine alpha, and that's a 0, and it's a 0, and it's a sine alpha, and 0, and cosine alpha. And then you guess what the z is. And boost, if I boost my system along the x-axis, B for boost along x-axis, then we have the gamma and the velocity and all this, but there's a very cute way of writing it. If you if you say gamma, gamma is really 1/1 minus v squared over c squared. That's the gamma factor. If you write this as cosine hyperbolic of some other parameter, then called rapidity, then the gamma times v over c is the sine. And if you look back in your Lorentz transformation in the boosts, you have these two combinations, gamma and gamma v over c. And so the whole thing looks really like those matrices, just with the cosine hyperbolic here, and then cosine hyperbolic here, and minus sine here, and minus sine here. This is in x and t, the boost in x, x and t, and it doesn't care about y and z. So this is one boost. It wasn't so hard to write the matrix representation explicitly if I only have one thing, like rotating in this plane or in that plane. In the notes, there are all the matrices, but they are not super important. And now you can combine them to get the full. So you get lambda of g basically, which is really a lambda of alpha x, alpha y, alpha z, eta x, eta y, eta z. All three. This is a choice that I'm making. I want dz alpha z, dy alpha y, dx alpha x, b. I forgot what I wanted. Forward or backward? No, backward because it is backward. So z eta z b y eta y bx eta x. So this means you have your poor little chair there, and first you throw it in the x direction. Once it's passive. Sorry, the chair is safe. I am going in the x direction, then in the y direction, then in the z direction. Then after I've all done this, I rotate around my x-axis. Then I have a new x-axis around, and then around, and I also have a new y-axis. Around the new y-axis, I rotate. I rotate, and then I rotate around what was the y-axis, and then I rotate around the z-axis. This is what pilots do. This order thing here. This is pilot. It's called roll, pitch, and what was it? I looked it up. Jaw or something like that, right? What was it? Yes. In German, rollen, nicken und gieren. So if you have your plane, where's my plane? This is the plane, like this. It flies like this. First it rolls. So that's around the first axis, and then once you have rolled where you want to go, then you can pitch. Pitch is so it made more sense nicken, right? In German it's nicken. Once you have done this, then you nick, right? The literal nicken. So you go this, but then you can, after we've done that, you can also go this way. You want to become a pilot now? You have the wings, the flaps, the wings which roll you, and then you have the flaps in the back of your plane, which brings you up and down, and then you have the side, which does this. So these three rotations, one at a time, bring you in whichever position you want to fly. Yeah. You can also, if you're spinning top, you would have talked to Euler and pick different things. So Euler angles would be like this. They would be z first instead of x, and then this is your spinning top. This corresponds to the spinning motion. Then you have over around the x-axis. This is the precession because the thing goes around. If there's gravity, and then the z again with the notation. So you can have even both the same. And it's still good. I could have copied this in there. It would just be a different parameterization of what I have here. So these matrices, all of these matrices are one parameter families. They go through this point. Because if I set alpha to 0, I have an identity matrix. If I set eta to 0, I have an identity matrix here. So all of them go through here in the different directions. So this is now varying alpha. And that's why it's a 6-dimensional potato, because they go all in different directions. Oopsie. That was too far. And had I chosen something else, I'd be going somewhere else, right? Now, that wasn't so hard after all, right? I said it was so hard. It wasn't so hard to find an explicit matrix representation. See, I punched this into the computer, and it wasn't so bad to write these 6 matrices and multiply them together. It's so long, I wouldn't want to write it down, but it works. What is really hard is if you take 2 of them, right? You take lambda with all of this, alpha x to eta z, multiply it with a different one, x eta z. And if you want to know what are the alpha x double prime to eta double prime as functions of these. So this is a function, this alpha x double prime is a function of all of these 12 words, and that would be in this. So that's why we're not going to do this, but we will look at the tangent space to our manifold there, to our group in group, at the identity. So we'll just go here. So we will construct tangent vectors. So one you can see that's to the red curve, and then one to the yellow curve. And these are literally vectors, which you know, in the sense of vector space, you can add them and multiply by scalars, and you have a basis, and all of this. It's a very simple addition of them. While that is not a vector space, the group is not a vector space. The group is just awful multiplication. So combining 2 group elements is a nightmare, while combining 2 of these tangent vectors is simple. It remains to be seen whether it will lead us anywhere. Answer is, it will lead us to the end. Yeah. Now define, it isn't obvious, right? Sophos Lee was working on this for years. What's the story? He published this in Norwegian, and then people didn't read it at first. So now define tangent vectors. And I'm going to define my tangent vector J, K, as the derivative of the d x of all the. Am I going to write g here? No, it's just the alpha in it with respect to alpha, and then I'm going to set alpha to 0. This is the tangent vector, right? This is how it changes. You have a curve. You have a curve. This is the curve. You differentiate, you get the tangent vector, right? Makes sense. That would be what a mathematician does. And the physicist multiplies in either minus I. Because I guess they turn out to be antisymmetric and the physicists can't deal with antisymmetric matrices, so you're not gonna there. And then it's antisymmetric and imaginary, and then you can call it Hermitian. That's why we do that. And the J is for the letter D, the rotation, the tangent vectors to the rotation are called J, and the tangent vector to the boosts. Oops, this is K, this is K. K is X or Y or Z. I do this for all three. And the KK is minus I D, what was that? E K eta with respect to eta to 0. So that's the tangent vector there. Now, what are these things? Let's do an example. Jx. So if I do Jx, I have to differentiate this thing with respect to alpha, all constant. So nothing. Cosine is, I guess, minus sign, but then I have to set it to 0, the alpha, and then it's also nothing. And now the sine is the cosine, and 0 is 1. So it is 1 with this minus I is minus I. And then here you get I. So that's how your tangent vector looks like. Now we say it's a tangent matrix. No, it's a tangent vector to a manifold of matrices. Awful, right? So it is all these points were matrices. So your tangent vector is a matrix. But still, it's tangent to the curve that's parameterized by this alpha. That's your tangent vector. And the Bx is what is that? 0, lots of zeros. And now sine is cosine, but it's minus 1, and this should be I and I. Well, I don't know what the physicist says now, because that's not Hermitian anymore, goodness gracious, but still.
It's Kx, right?
That is probably K, thank you. Yes. Well, the physicist didn't think far enough, I guess, because he didn't think he encounters a boost. Anyway, that's the. So now this is a vector space. Oh, what? No, hold a minute. Don't go away. So all these arrows are these matrices, and you have more. You have also J, Y, and J, Z, 6 of them. And if you wanted, you can combine them in any other ways. You just like the vector space, you add them. And if you add them, then you still have, well, what do you have? What do you have? So, you can go back. If I invert these relations, let's call this like abstractly, because I want to have both cases. So the tangent vector T is minus I d lambda of theta d by the theta theta equals to 0. So this this is just the structure there. And if I invert it, I can say lambda of theta is equal to I theta t. Yes, I have to say what well, that satisfies this, my initial condition. And I want lambda of 0 to be the identity, because I want to go there. So then I have this thing. So if you pick whatever element of this vector space, of the tangent vector space, you can exponentiate it in this way, and you get a 1-parameter family. of, you get your own curve, right? If I say, I add these two things, this is the Jx and this is the Bx, say, and I add the two, and then I get this, and exponentiate, so I get a new curve in this thing. And this creates a one parameter family. One parameter family of Lorentz transformations, based on T, because T gives you the direction, the tangent vector, and therefore you call this T the generator. Exactly, I heard it. I did hear it. Based on T, so T is therefore called generator. I had to really be careful not to call these things generator all the time. I had to say tangent vectors, but these tangent vectors are the generators of the group elements. You generate it in that way. You exponentiate them and then you do this. And now, just to wrap this up with a comment where we are going, this vector space here is not just a vector space. It is more. It is a vector space with some stuff, with some extra structure, namely a product. It's an algebra. We will tomorrow turn this vector space into an algebra. An algebra is a vector space where you can take two vectors and multiply them. Not in the sense of a scalar product, that it could be four, but because the scalar product ends up, it produces a number, not a new vector. So it's vector times vector is a new vector. And so this, we'll find this. And that will basically give us the multiplication law in the group, but simpler. We're still in this algebra, in this vector, in this nice vector space. Yeah, well, I was going to say where we're going with this, we'll construct the representations of the Lorentz group. The path is through this tangent space, through the algebra, finding representations of the algebra and then lifting them by using the exponential to representation of the groups. And what we will then take away from there, the next week, is this table of all these representations. And we have the scalars in the table, we have the spinors for the spinning on half particles, and then we have the vectors for our photons. Yes. Before